Hi, welcome to Raw Math. Today I'm doing a series of videos on scatter plots and lines of best fit. This question starts off just saying, draw a line of best fit. All right, just so you know, when I think about a line of best fit, I'm talking about an eyeball line of best fit. So I'm not going to do any crazy equations. I'm not going to go to Excel. When I do an eyeball line of best fit, I have two criteria. The first one is that the line goes in the direction of the data. I'm starting with direction of the data because sometimes students get so fixated on splitting the data that they count and they do a perfect perpendicular line to split it up, and that's not really going to represent the data. The second one is generally splits the data. Now I say generally because I can't go straight down the middle of this because the ends are going to kind of bring down the data. We kind of have to think of this would more likely be modeled by a nonlinear. It looks very curved, but if we're going to do a line, that's what we're going to try to do. We have to generally split the points, and it's going to be hard to be completely precise. So when I do this, what I'm going to do is I'm going to try to go in the direction of the data as best I can and try to split the data as best I can and get a line of best fit. I do hit some data points. I actually hit 3 of them. Doesn't matter. I don't care about the data points. So much so that when I come through and I pick out points, I'm really looking for nice grid spots. So like this right here looks like a good point on the line. It also looks a little bit like a data point, and the data point is making it hard to see. Maybe the line is going just below that point. Okay, here's a good one. It's going smack in the middle. That data point is 2.5, 8. My second data point that I'm going to use, I'll use this one right here, which is 12.5, 1.5. Decimals. I will say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ton more. I wouldn't use this on a test. I might actually move it up a little bit. It's just, there's too many below. It's hard with a pen. I can't erase very well. I'm just gonna tap that up a little bit. I think the direction was okay. Let's see. That looks a little better. So instead of these points, let's pull some out of that one. This time we have this point right here, which is 4.5, 7. We have, let's see, we have this point right here. That's kind of nice. That's 10.5 and 3. Let's use those points instead. That looks a little bit better. That one might be a little bit high, but in general, like with the curve, like I said, it's a little bit difficult to find. All right, we'll do those points instead. With a pencil and eraser, it's a little bit easier to get this correct. Okay, and I'll also tell you every time I do this problem, my line of best fit is a little bit different because it's not precision. It's a general line of best fit. All right, it says find 2 points. That's what we have. Notice the ordered pairs, parentheses, comma. And then it says, find the model equation, same idea. To find a model or an equation, we start with the slope. So slope is 3 minus 7 over 10.5 minus 4.5, which is negative 4 over 6. And God, you just want to reduce that fraction, make it a beautiful fraction. The problem is this is data. This is not precision, and fraction implies precision. Moreover, I'm going to take that one more step and just say negative 0.67. You notice this is just an estimated line. It's just an estimated slope. Fractions are not a good way to represent data because it tells a story. It tells a story that everything is precisely that. But you see all these points. Very few of them are on the line. We've had 2 different lines that could possibly work. In either case, it's close. We're guesstimating the points, we're guesstimating the line. A fraction is not appropriate. Okay, equation of a line. y minus 7 equals negative 0.67, x minus 4.5. I'm going to distribute my slope in. Y minus 7 equals negative 0.67. I don't know why I have that line above it. X plus, so when I put this in my calculator, I get 3.015. I'm just going to keep it as 3. Simplify this problem a little bit. If I was rounding to 2 decimal places, I probably should say 3.02, because this is 2 decimal places, this is 2 decimal places. That becomes my significant digits. We add the 7 over. I will keep that 02 in there. And I get y equals negative 0.67x plus 10.02. If you don't know how to write an equation of a line, and that part is what's confusing you, I do have a whole playlist and a bunch of videos on how to write an equation of a line using this method versus the more common plugging into y equals mx plus b. This one gives you an equation right away. You're just then manipulating it algebraically to get it into the form most instructors want. Okay, it says use your model to predict the value of the car. 15. I'm gonna change this to 14. I meant to do that. This is all data. It kind of has that negative slope. I think 15 is a little bit beyond what this graph is going to give us. So I just want to go 1 year out past the graph. Okay, so if I do prediction of a 14-year-old car, I say y equals negative 0.67 times 14 plus 10.02. And I'm just going to plug that into a calculator, and I'm going to get y equaling 0.64. Okay, one of the common mistakes both in A and B that I see is the answer then becomes 64 cents, which makes no sense. I mean, you might be thinking, hey, look, it's going down. 64 cents makes sense. It's a hunk of junk. But this says that the data is in thousands of dollars. You might not be able to read it that well, but that's what that says, thousands of dollars, which means I need to multiply by thousands of dollars to get that the value of the car after 14 years is $640. All right, next, and we got to remember that translation. Next it says, according to your model, what is the age of at what age is the car worth $8,500? So your first instinct is to say, haha, I'm putting this in for y. So negative 0.67x plus 10.02 is equal to 8,500. But we seem to have a problem with that since as soon as you subtract and divide, you're going to end up with a negative number, which is not going to help your cause at all. So what I need to do is remember that thousands of data, thousands of dollars. I need to take the 8,500, divide by 1,000 to get 8.5, and then I can say negative 0.67x plus 10.02 equals 8.5. Subtract the 10.02 from both sides. I have negative 0.67x is equal to negative 1.52. And then I'm going to divide by the negative 0.67. And I'm going to get that x is equal to 2.2. If I round to 1 decimal point. If I go to 2 decimal places, it's going to be 2.27. Either are fine. So it says, at what age is the car worth $8,500? It says our ages are just numbers because we don't have a year to add to this. So I'll just give my answer. The car is worth $8,500 after 2.27 years. And I am totally willing to leave that as a decimal because 2.27 years, we could figure that out. I mean, we say when we're a kid, we're 2.5 years old, or apparently, as I said, 2.5 because I didn't want to give anything up. So this is fine. Years can have decimal points. All right, I hope you've enjoyed this video. Please subscribe to my YouTube channel, like my Facebook page, and I'll see you on the next video. Thanks.